This video is designed to give you a little guidance on today's lesson, which will involve exploring the shapes of the graphs of parent functions. We talked about this a little bit in the last unit when we thought about what type of equation might possibly model a certain situation and graph. Today we're going to really dig deeper into what each parent function looks like graphically and why. And the big idea here is that because the operations in each parent function is different, when we choose inputs, we're going to get unique outputs because of the operations in that parent function. And as a result, we get a uniquely shaped graph when we plot those inputs and outputs. So to give you a little more guidance, let's actually start here. Notice this little hint at the top that says try using -3 through 3 for your inputs, unless you think the function is better suited to different or better inputs. But in general, -3 through 3 might be a good starting point. Okay, let's take a closer look at the exponential growth function, something you've visited in the past, and that's in the bottom right corner of this first page right here. So I'm going to zoom in just a little bit and we can take a closer look at the exponential growth function. So something you would have learned in a previous math class is that exponential functions have x as the exponent because we're repeatedly multiplying by some base or multiplier. In order to grow, that base has to be bigger than 1. So for this problem, it might help to choose 2 as the base. It's bigger than 1, but it's small enough that our points might still fit on the graph. So first thing that we can do here is pick our inputs. So I'm going to go ahead and just choose that standard -3 through 3 for this graph. And now we can take those numbers, -3 through 3, and one at a time input them for our x right here. And when we do so, we'll end up with outputs. You can see that when we, for example, plug in 2 to the third power, plugging in that 3, 2 times 2 times 2 is 8. And so the output is 8, meaning that 3, 8 is a point we can now go plot on the graph. That's going to be off the graph just a little bit. 2 to the second is 2 times 2, which is 4, and so forth. You would have learned in the past anything to the 0th power is 1. You also would have learned that a negative exponent is really just the reciprocal of the positive version of that exponent. So 2 to the negative first is the same thing as 1 over 2 to the first. 2 to the negative second is the same thing as 1 over 2 to the second, or 1/4. So we keep getting these reciprocals, noticing that as we move to the right, the outputs are getting bigger and bigger. As we move to the left, the outputs are getting smaller and smaller. Although notice they're never going to quite hit 0. We just keep taking half of the previous one as we move backward, just like we were doubling the previous one as we move forward. Now that we have our table of values, we can take those points and plot them on the graph. And so as we plot the points on the graph, we start to see them forming this nice exponential growth curve. And notice how we talked about how these outputs are never going to quite get to be 0. We can see that on the graph here in the form of an asymptote. The y values are getting closer to 0, but they're never quite going to hit. So now we have this parent function for what an exponential growth curve looks like. At this point, now that we're looking at the graph, we can think about the domain and range. We'll review this in much more detail in this unit, but for now, the domain is all the inputs that we see on the graph, so we can look left and right. And in this particular function, the graph goes left and right forever, meaning we can input anything we want. The range, notice we're never getting outputs that are negative, so the range is only outputs bigger than 0. And locator point, we're really just trying to pick one point on the graph that might be a good point of reference if we wanted to try to explain to someone where this function sits. And I'm thinking this y-intercept here, this coordinate 0, 1, might be a good locator point for this function. It's kind of that center of the graph that would help us think about where it sits in the coordinate plane. So now we can fill in this section that talks about domain, range, and the locator point. Domain is saying that x can be anything. X is an element of the real numbers. We can also use interval notation and say that it goes left forever toward -infinity, and it goes right forever toward infinity. Our range was our outputs. We said y is always above 0. And in interval notation, that would say that 0 is the lowest it goes, soft bracket because it never hits. Infinity is the highest it goes, and we never get to infinity either. And then there's our locator point, 0, 1. Okay, let's take a look at one more together right now, and then the rest of this will be yours to try on your own. One other graph I'd like to look at is the log function, probably one of the ones that everyone finished last year feeling the fuzziest about. But the key thing is that logs are just the inverse of exponentials. And one thing you would have explored in the past is that inverses reverse what the input and output do. So for exponentials, if I input a -3 and I output a 1/8, the log function should do the opposite. It should input a 1/8 and then output the -3. It should just get me backward. So I'm going to go ahead and scroll down here now to the last, actually we're going to have to go to the third page here. This is the very last function in your packet. You can notice that the last two are crossed off for now. So what I did right here is give you this function. Instead of y equals 2 to the x, now we have y equals log base 2 of x. And so it'll be important here to remember that this is really just the inverse of y equals 2 to the x. So what that means is all those outputs that we got for y equals 2 to the x can then become our inputs for this log function right here. And our output should really just be the original inputs that we had used for that exponential function. If you want to see what that would look like as far as actually inputting these numbers, here we go. The log function takes log of, in this case, 8, and gets us back to the exponent that would have gotten us there. Log base 2 of 8 is 3, because 3 is the power that gets us from a 2 to an 8. You don't really need to think that much about logs right now. We can just think about how logs and exponentials are inverses of each other. So the exponential function had 3 for an input and 8 for an output. The log function is the opposite. 8 is now the input, 3 is now the output. And now that I have this table of values, I can plot all those points on the graph, and we end up seeing this perfect mirror image of the exponential function. Instead of a horizontal asymptote at 0, now we have a vertical asymptote at 0. Instead of the locator point 0, 1, now we see this coordinate 1, 0 on the graph. Everything is backward because they're inverses. And I get this shape right here that shows this log function. Now that I have the graph, I can think about domain, range, and locator point. So we can see on this graph that all the x values are always positive on this graph. It doesn't make sense to take the log of negative numbers because you can never output negative numbers in an exponential. The range is anything. This graph goes up and down forever. And the locator point, like we already discussed, is 0, 1. Hopefully this helps get you started. For the rest of these functions right here, I would highly recommend just going back to this idea that -3 through 3 is a good starting point, unless you think those inputs don't make sense. And then your job is to fill in the outputs, plot your points on the graph, and then try to describe them by thinking about domain and range.